Are we going to wait until about 5 past? See who comes in, or
I'll let the ones who come in like later. I'll let them in. So I think
okay.
probably.
Should we get started then?
Yeah.
Okay. All right. Well, hi guys. I'm Richard. I'm another member from the committee, and in this session 3, we'll be going over like electrical wiring and some like familiarization with the sensors and the motors. So hopefully we'll actually, sorry, I should probably start off with if you have any questions whilst I'm going through this, stick them in the chat. I have it up and open in another window over there, so I should be able to answer them as we go along. Okay, so first up is our kit list. So hopefully you've all got your kits by now, with all the 3D printed parts, electrical components, and so on. We do believe that we have forgotten to send out the USB cable for programming the Arduinos. This is like a USB-A to USB-B type connector, like shown here. We will get them out to you as soon as possible. But in the meantime, a lot of printers and things use this. So if you do have a cable for a printer you're using, you can quickly nab that to print the Arduino until we get the cables out to you. And also, as well as this, you might be missing a 9-volt battery connector. Please send us a message if you are, and then we can get it out to you. Another heads up as well, we are expecting these kits back at the end of the course sort of thing. So, you know, keep them in good condition. Don't try not to lose any components or anything. Okay, so first up here is our sort of suggested wiring diagram. So at the end of this, we will stick some demo code on the wiki, or it may already be there, which shows you how to use the various sensors involved in this project, like the ultrasonic sensor, the light sensors, the inertial measurement unit, and so on. This demo code is set up with all the sort of pin definitions as is shown here. So we know this setup works, and this is probably the best way to do it. Though, of course, you can customize it if you want. There's a few things to keep in mind if you don't keep it like this. So on the Arduino, certain pins can do certain things. So for example, hopefully over here, you can see, I know it might be a bit small on your screen, these are pins labeled A0 through A5, and these are all analog pins. So on these pins, you can read like analog values. So, you know, from 0 to 5 volts, if it's about 3 volts, it'll give you a value of say 600 or something along those lines. These other digital pins will only tell you whether the pin is high or low, so above 2.5 volts or lower than 2.5 volts. As well as this, there's a variety of other functions that can only happen on certain pins. So there's these pins denoted with a little tilde before the D11 here. These are PWM pins, and we'll talk about PWM a bit later, and so on. You need to keep these things in mind when connecting up, say, the motor controllers here. So a lot of the work you'll be doing will be on breadboards. I imagine some of you have probably encountered a breadboard before, but for those of you who haven't, it can be a little bit confusing. So the top rails here and the bottom ones are connected horizontally, so all the way across, so that you can use these as power rails. So you'll stick your 5-volt output from your Arduino into these top 2 rails, and your ground from the Arduino into these bottom 2, and then sort of as shown here, if you want to have an LED, you can quite easily set it up like this. And all of these sort of vertical sections here are individually connected. So you can see the end of this resistor and the LED are connected in this case because they're in the same sort of little row. But for example, these columns here aren't connected to each other, but they're only connected among these 4, 5 pins. This central channel is quite useful because you can connect any chips you're using across it. And as these 2 sets here aren't connected, you won't sort of short the opposite 2 pins of the chips. A big important thing was breadboarding is to color code your wires. So, you know, 5 volts or positive power should be red, ideally, or something along those lines. Ground should always be black. And then like specific types of data, from there on, you can sort of decide for yourself. But, you might say all the ultrasonic sensor data lines are going to be orange, all the light sensor lines are going to be blue. And it really helps when you're trying to debug, because there will be a lot of debugging to do. So the first component we're going to go over is the motor driver, possibly the most important thing in this. So a motor driver is required to supply enough current to the motors that we're using. So, theoretically, you could drive a little motor straight off the Arduino. It's got 0 and 5 volts. But the problem is the Arduino itself is only able to supply quite a small amount of current, which means you can't get a lot of power out, which means, the motors you'd be driving would be very low torque and wouldn't be able to go very fast. So this motor driver, it takes some outputs from the Arduino and takes the power straight from the AA batteries and use it to run the motors. So now instead of getting, say, 10 milliamps from the Arduino, you can get a whole amp from the AA batteries to run the motors. So you can run motors of a proper size. So there's a few things to keep in mind here. So the in pins, you have like A in 1, A in 2, B in 1, B in 2. I should mention these are dual motor drivers. So for each one of these, you can connect 2 motors. That's what the A and B part is. And the in pins tell you sort of the effect it's going to have on the motor. So if you bring both of the in pins low, as you can see in this table up here on the top right, it will just leave the motor idling. It's like there's nothing really connected. If you bring in too high and keep in 1 low, it will drive the motor counterclockwise, and vice versa, in 1 high and in 2 low clockwise. And then finally, if you bring both of the pins high, it will sort of run current through the motor such that it actually forcefully brakes. Most of the time, you're not going to need this, but if you do use it for only a very short period, because it's almost like shorting the power supply across the motor. Oh, sorry, as well as this, I should mention these standby pin here. You need to bring this high when you're using the motor driver, otherwise it won't do anything. So connect that to 5 volts. So what I mentioned on the previous slide was that these in pins control the direction of the motor, and the power is controlled by the PWM on these PWM-A and PWM-B inputs. So, the power or the speed or whatever. So what is PWM? So PWM stands for pulse width modulation. It's, you've got your standard square wave here, showing you a 50% duty cycle. And if you vary it such that the sort of width of this high peak changes, that's called pulse width modulation. So the frequency of the square wave stays the same, and it's just the time on versus the time off that's varied. And generally in electronics, this is used as a sort of digital way to output an analog value. You can imagine if you sort of average these waves out over time, if this peak voltage was 5 volts, this 25% duty cycle one would be average out to be about 1.25 volts, 50% would average out to be about 2.5 volts, and so on. So in this case, it's used to communicate the power demand to the motor drivers. So you can think of it as a 0 to 100% thing. If you just give it a constant low, it will not drive the motors at all. If you give it, say, 50%, like shown in this bit here, it will drive them at 50% of its maximum power, and so on. The next thing we have is the IMU, or the inertial measurement unit. So this is used to get a bit of more of an idea of sort of what's going on with the robot at the moment in terms of like movement and things. So it includes a gyroscope and an accelerometer. So this gyroscope senses changes in like angular position or angular velocity. So you can integrate this to find your angular position. So you're heading like, north, south, east, west, whether you're tilted up a slope, down a slope, and so on. The accelerometer senses acceleration. So if you're, obviously if you're starting to suddenly put a lot of power through your motor, you should feel the acceleration whilst you're going forwards. And this accelerometer also measures gravity, of course, because gravity is just acceleration. This communicates with the Arduino over a protocol called ISquared C. We'll go over that in a second, but you don't really need to worry too much about this unless you want to go a bit further with this project, as the library we provide handles all the details really. So just as a quick overview, what is ISquared C? So it's a two-wire communication protocol where a master device can talk to many slave devices. So these could be many, many sensors. So, in this case, we're only using the IMU over ISquared C, but you could have I2C based light sensors, I2C memory, and things like this. And all of these can communicate using the same two wires plugged into the Arduino. So it saves a lot of space and pins on the Arduino. In this case, the Arduino is the master and the IMU is the slave. And generally, I2C is used for short range communication. As I said, you'd be using this to communicate within a robot, not across multiple robots or things like that. So a little bit of detail. So SCL is a clock signal that's generated by the master. So this is just a square wave like we saw before that constantly goes high, low to sort of synchronize all the devices so they know what frequency they're talking at, and also like the phase offset. SDA is the data line. So devices take turns putting data on the line by pulling it low. So the master will say, okay, slave device 1, I want to have this reading from you. Then the master will let go of the data line, and then the slave can say, okay, this is the data coming out. And then it will send an end bit, and then the master can start talking on the data lines again. Next up is the ultrasonic sensors. So you can measure distance to these up to about 2 meters, I believe it is. The way it works is reasonably simple. It sends out ultrasonic pulse, a pulse of audio above 20 kilohertz when the trigger pin is pulsed. And then when it receives a reflection on the sort of sensor, on there you can see there's one transmitter and one receiver, it will pulse the echo pin. So using the microcontroller, we can measure the time between when we send the trigger and when we receive the echo. And using the roughly constant speed of sound, we can convert this to a distance. I'm going to say again, you don't have to worry too much about this conversion. We have a library that handles all of this. A few things to keep in mind is not necessarily super relevant to what you're doing now, but depending on this type of sensor, it can have quite a wide range of distance measuring or quite a narrow range. So if you had a small gap in the wall, it might not sense behind the wall. It might actually just sense the two sides of the wall next to it, for example. Yeah, as I said, you use the library HCS-R04 by Martin Sosik. There's multiple libraries available for this. They all work very well. It's quite a simple library, but this code fragment on the right is one based on using that particular library. They'll all just have a little bit of different syntax to interact with them. By the way, next week, someone will go through a bit more in detail of the programming, so this is the only code fragment I'm going to keep in here for the moment. But basically on Arduino, you have a setup function and a loop function. Everything in the setup function gets run when you reset or start up the microcontroller. And then once that's all run through, everything in the loop gets run repeatedly. So in this case, we're starting the serial connection to the computer. And then every loop, we're reading in distance in centimeters and just printing it out to the computer and waiting a second. The sensor has quite a lot of random fluctuation because it's quite a cheap sensor in a way, and there's lots of random variation. So averaging will be your friend. So if you want to have, say, an array of 10 values and average them all out so that you get rid of any fluctuations, as well as this, the sensor will return a -1 if no echo is received. So you might want to discard these measurements. Next up, we have servos. So servos on the robot, there are two little servos controlling the gripper. They're basically small motors that can have their positions quite accurately controlled. In these cases, these are quite small servos, but you can get servos that are very large that can do a very high amount of torque. So the position of these servos is controlled by the PWM value sent by the controller. So again, this is the 0 to 100% value we looked at before, and it will map that 0 and 100% value to its sort of limited range of movement. So in this case, these servos can only go from 0 to 270 degrees. So you will, 0% will map to 0 degrees, 100% will map to 270 degrees, and it will do its best to hold it in that position. They can be quite delicate, so don't do anything too talky with them, and because they can quite easily break. Much like the motors, it's generally best to connect these to the AA batteries rather than powering off the Arduino, because they can use a lot of current if you're doing something hard with them. And yeah, finally, the orange wire on this is, you can find this all online, Googling it. But just for quick reference, the orange wire is the PWM signal from the Arduino, and red and brown are the power, positive and negative, respectively. And you can also see on the right here that we have a couple of different heads you can pop on to the end of the servo for doing various different tasks. Now we have the light sensor. This is a very simple one, so I won't go into too much detail. I'm not sure if this is the exact light sensor you have in your boxes, but honestly, it should be basically the same regardless. They measure the amount of reflected light coming back from the onboard LED. So you can imagine if you have a black surface, there's not going to be a huge amount of reflected light, versus if you have a white surface, you're going to get a lot of reflected light. These can be used for line following, for if you have a bit of white tape on a black background, you can see when it's on or off the tape, so you know where to drive. And also for like edge detection. So if you're driving around on a table, when you get to the edge of a table, if you have your light sensors ahead of where your wheels are, you can see that all of a sudden no light is being reflected. And this will tell you, stop, reverse, go somewhere else. Again, 3 pins, signal and power pins, positive and negative. Okay, so that's the end of the sort of introduction to all the individual components. I've got some top tips here. So as I said before, color code your wiring. It really will make it so much easier to debug. If you're just starting with electronics, I feel sorry for you guys this year, because we're not going to be there with you in person to help you out. Next is make sure all the components share a common ground. So this is a bit of a technical thing, but basically, as you're using sort of 2 separate power supplies, you're using the 9-volt battery plugged into the Arduino to power the Arduino, and the AA battery is to power all the motors. You need to connect both the ground of the 9-volt batteries and the ground of the AA batteries. Otherwise, your voltages aren't referenced to each other. It's a bit of a long thing, and I'm sure you'll learn a bit more about it in 1A electronics. Next up, when you're storing or not using the kits, unplug the 9-volt and AA batteries, or you will run them down. It's not really a fire risk or anything, but it's going to be a bit of a pain in the ass if you find out your 9-volt batteries are out. Next up, test all of your components individually. So I'd advise writing a bit of code where you can just plug in an ultrasonic sensor and see if it's working, plug in your light sensor, see if it's working, and so on. Again, it makes things a lot easier to debug rather than just having one big program. All you know is, okay, my robot's not working. You don't know what bit of it isn't working. And finally, Google all the things. Honestly, most of electronics and everything is Googling data sheets, Googling Arduino forums and things. If you have a problem, it's almost certain someone's had it before. So spend a lot of time Googling. Googling's a really useful skill. I can't stress that enough. But if you do have some trouble and you can't find the answer from Google, then ask your mentors. I'm sure we'll be happy to help, and ask me as well. So that's the end of the prepared content for the moment. Yeah, I'll open the board to any questions, and I think Jerry has something to say as well.
Right. Just like regarding recycling the kit, what Richard means is all the electric components, like the light sensors, the ultrasonic sensor, and of course the Arduino Uno board. But as for the wires and like the jumper wires and the 3D printed parts, we won't ask that from you. So don't worry if you lose a wire or something like that. Like those are cheap and replaceable. And also regarding some questions I've got, during the week, like someone asked me about like whether they can get like customized parts or like extra parts. And so it works this way because budget wise, we don't really have that like that budget for you to purchase like electronic components, and it will also cost a lot of time to get it shipped, to get a single component shipped. So that's probably like we can't cover that for you. But for 3D printed parts, the society does have two 3D printers, and they are in Kai and Peter's room. So if you would like to print some like small components, say for example you want to customize the arms to grab the ping pong ball, you can do that. Just send them an email, and with your G-code file of the components that you want to print, and you have to collect it from them. And also they will inspect whether it's a reasonable print. Say for example, we wouldn't expect you to design a chassis with using a to be 3D printed. Yeah. And other than that, yeah.
Can I just interject there for a second? So if you're sending over a file for 3D printing, send both the STL and the G-code file, because we'll need to slice it for our specific printers.
Okay, yeah, good point there.
Okay.
And yeah, we'll be open for any general questions.
Yep, okay, so Ewan has a question. So do we get an electric schematics? So yeah, as someone's just messaged me asking for the slides. The slides are all going up on the wiki.
Yeah.
So previously in the presentation, there was a bit of a electrical diagram here. So this sort of tells you broadly what to do. I'm sure at some point we will upload a more detailed one if you need it. But yeah, this will be up on the slides on the wiki.
And in case you haven't, you can go and download the Arduino IDE now from the Arduino website. You can just Google it and you'll find the download for the Arduino IDE and other tutorials if you have never encountered it before.
Yeah.
And I think it's got schematics for many of the components as well. But if you know what the component is called, just Google it and you'll get it.
Yeah. Yeah, but all the part numbers are in the kit list here. So if you Google them, you should be able to find some more information about them as well. Find the data sheet and things like that. But yeah, don't spend, weeks struggling. If you can't get it working, send us a message. We will sort you out. And if enough people send messages struggling with it, we'll send out something to everyone, because we imagine you'll all have similar problems. Okay.
Right. Also, another point. Can I share the screen?
Yeah, go ahead. I'll stop sharing.
Yeah, just so you know that we've updated our Minibot competition rules, so you can have a look at the criteria for scoring and basically how the competition will take place, and also some details about the arena. As for the arena, we are thinking of splitting the arena into like 8 parts, so each of the team can get some tiles for their robot to work on. And also the internal competition this term will be on a arena of like 2 times 3 tiles. So, but the shape is like it won't be available to you before the match, but you can try on some of the combinations. The details are all here. And also on the wiki page, we've uploaded your teams and supervisors you can look for. So in case you got any questions like during the week, you can just leave a message on Slack or send an email to us. Yeah.
Okay. Well, I think if there's no more questions, yeah, next week will be, I believe, Jacob doing a introduction to Arduino programming. In the meantime, if you manage to find a USB cable, have a little play around with the Arduino and some of the sensors. That'd be really good. Get the Arduino IDE downloaded. There's lots of good tutorials, introductions to Arduino online as well, which would be good to look at in the meantime if you're keen. And yeah, I guess that's it for the session, Jerry.
Yeah, we can stick around a few minutes if anyone has questions. But otherwise, it's like the main work takes place in your own time. It's not like during the sessions, since we can't really do it like that this year.
Yeah. Okay, thank you very much, guys. Right, I think I'll drop off now, Joe.
Yeah, no problem.
Okay, thank you, guys.
Thank you, Richard.
No worries.